Hello scholars, Mr. Hinkle here, and today I want to briefly introduce this topic of geology. Geology, it is all around us. It is everywhere we go. It is underneath of our feet. It is surrounding us. It is our home. Now, geology is the study of the earth. Geological processes are systems and actions that are happening on the earth through scales which we can perceive and through which are almost imperceptible. Kind of like these rocks, how you have the red sandstone that has stratigraphic beds in one direction. Here we go. Handy dandy, because I don't think you can see the laser pointer. Stratigraphic beds in one direction, and then stratigraphic beds in another direction. How did that happen? Geologic processes, of which we will be getting into in this course. So, our objective for this lecture is to introduce the field of physical geology. This is Geology 1, Physical Geology, and we will provide a comprehensive overview and understanding of fundamental concepts and principles encompassed within this field of physical geology. So let's start here our discussion on physical geology. So today, geology is a science. The systematic approach for understanding the governing processes to natural phenomenon in our known universe. Now, this scientific study of Earth looks at the structure, the composition, the processes, and the geologic history all the way from the beginning of Earth until now. And it investigates Earth materials, that's a fancy way of saying rocks, that make up the Earth, Earth processes that shape and carve its surface, and Earth system changes that have occurred through a vast amount of time, in fact 4.54 billion years old. So this is a good place to start. What is geology? Geology is science. It's the science of our Earth. Who studies geology? A geologist. Da, 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 da. Do you see the geologist here? This is actually me in undergraduate. I'm like 20 years old there. You can't really see because of the shadow over my face at the Devil's Post Pile in Mammoth. These are big columnar basalts, which is a fancy word for lava rock, things we'll get into. And this is basically a geologist in training as opposed to the geologist you see before you today. But I would like to argue the fact that as you go through this course, you are a geologist, because a geologist is a scientist who studies the earth, and in this course, which is a science course, you will be studying the earth, and so you are a geologist. And what do geologists do? They analyze rocks, minerals, fossils, geologic features to develop interpretations for how our earth formed through time. Work happens out in the field, which means out in the world. Happens in the lab, through the use of various scientific techniques and principles. So, geologist studies in the field and the lab. And if you are to become a geologist, this is where you will study, probably in both. You'll have field work and you'll have lab work. You'll work in the field to collect data, and you'll bring it into the lab to process that data so that you can understand how our Earth works. Geology is science, and it is the systematic method for looking at Earth materials and processes. Geology is more than just knowing how the Earth works. It has an impact in society, from natural resources to environmental degradation to natural hazards. Here we're thinking about resources. Let's look at gypsum for drywall. Let's look at oil and gas for energy. Let's look at environmental impacts, the negative effects of hazards, of bioremediation, of oil spills. Natural hazards, a big one, earthquakes, oh my gosh, tsunamis. So these things affect us. And if we look at the term geology, it's broken down to geo, which means earth, and ology, which means to think or reckon with, or the study of. Ology is the study of, its root is logos, to think. So thinking about the earth, geology. Kind of mentioned it, but geology is wildly important because everything on earth needs resources. Water is our resource. Where do we get our water from? How do we store it? Energy is a resource that comes from earth materials, from rocks deep down and within our earth. How do we extract these resources? How do we utilize these resources? And what hazards are associated with various locales based on the structure of our earth? So practically, we want to know about geology to know how to fuel and power our system and where the dangers are. Learning about geology helps us to understand the news articles because as you go through this course, you will notice that geology is in the news every day. Things are happening. Landslides, earthquakes, mudslides, floods, hurricanes, all of these things are connected. Geology connects humans, you and I, to our earth. So geology has different branches, and historical geology looks at the history of all things geology. Physical geology focuses on the understanding of earth materials and earth processes. Right? So we're going to say we've got earth materials, specifically the rock cycle, and then earth processes, and the big one that we'll talk about a lot is plate tectonics. The unifying theory for why we have mountains where they are, oceans where they are, how our landscapes transform through time, basically why the surface of the earth looks the way that it does, we could say plate tectonics. So when we're studying physical geology, we're looking at physical and chemical properties of rocks, the forces acting upon them, most importantly, water and tectonic forces, which I just talked about, and the processes that operate within or on Earth's surface that can be hazardous or beneficial for humans like you and myself. Early to modern, so this is a very brief overview. I love the history of geology, and history of science is one of my personal interests. Not only the science and how cool it is right now, but how did we develop this and how long has it been around? So ancient geology started, most earliest recorded history is around Aristotle, ancient Greek philosophy, when people were looking around and posing questions and philosophically discussing. The eruption of Mount Vesuvius is the first recorded geological report where it's a volcano that was erupting, and instead of ascribing deities and the wrath of the gods to what's happening in the mountains, Pliny the Elder actually wrote empirical notes on what was happening. Could say that was the first geology. 17th century, we have the 16th to 17th century, we have the scientific revolution, even science. It's a pretty young field. We'll talk a lot about science. And then with that, we've got some key figures. William Whiston tries to put age of the earth based on Noah's flood, connecting religious beliefs with this expanding view of the age of the earth and how it was changing through time. Steno looks at sedimentary rocks, develops Steno's principles of stratigraphy. James Hutton, our first slide, was on his famous outcrop at Sicker Point, where he said, there's no vestige of a beginning, no prospect of an end. Meaning, I don't know how long it took for this to happen, but it was a really long time. Earth time, deep time, is very, very long. Georges Cuvier started to look at fossils. William Smith connected fossils to sedimentary rocks to create a sequence of events that you could actually recognize through the geologic record. Charles Lyell was a great communicator of science. He wrote Principles of Geology and coined the term, "The present is the key to the past." Mary Anning was a very prominent fossil collector of her day. Alfred Wegener developed the idea of continental drift, which turned into our modern theory of plate tectonics. Ing Lehman looked at seismic data and was able to understand Earth's internal structure. And Marguerite Thomas Williams is the first African-American woman to achieve a PhD in geology. So a relatively young history of geology. It's been around as a science for the last 300 to 400 years or so. But a lot has happened to get us from there to here. So this is kind of fun to know brief history. The key areas that we will study: rocks. We'll really get into rocks. We'll look at rocks, we'll look at minerals, we'll look at plate tectonics, we'll get into geologic time, how we understand geologic dating, then Earth surface processes. This is rivers, surface water, groundwater, deserts, glaciers, and of course, because it's the biggest issue of our day, we will look at climate change, anthropogenic climate change, what it is, how it's happening, and what we can do, what you and I can do to play our part in halting further warming in the climate crisis that is occurring today. So, the most fundamental view of Earth materials is the rock cycle. And there are 3 types of rocks that are designated by form. We have igneous, sedimentary, and metamorphic. These are our 3 rock types. Igneous rocks form from magma or liquid rock in Earth's interior. They're broken down into pieces of smaller rocks known as sediments that then lithify into sedimentary rocks. Sedimentary rocks can be buried deeply where they change their form, their mineralogy, their crystal complexion, and metamorphic rocks can melt into magma. Now, you might say, oh, this is a very linear process, but actually, sedimentary rocks can melt, igneous rocks can melt, metamorphic rocks can become sediments, so can sedimentary rocks. Metamorphic rocks can then be further metamorphosed, so on and so forth. So it is a non-linear path. But this is a brief introduction to what we will spend a good chunk of time on: learning about igneous rocks and volcanoes, learning about weathering, erosion, sediments, and sedimentary rocks, discussing metamorphic processes, and tying it all together in the rock cycle. This is the movement of Earth materials inside and on the surface of Earth. Now, the theory of plate tectonics states that the surface of the Earth is covered by large, rigid plates of rock that move relative to one another, and they connect at plate tectonic boundaries. Plate tectonic boundaries are responsible for earthquakes and for volcanoes and mountain building. They do more, but that is a very brief description. And plate tectonics helps us understand why our Earth looks the way that it does. It is the fundamental unifying principle of geology and the rock cycle. So, plate tectonics, it's kind of a big deal. Earth's internal structure, here's another really big concept, certain things you will see me draw on the board a lot. The rock cycle is one of them. It is my goal that you learn the rock cycle and you have this for the rest of your life, so you will see me draw this a lot. Earth also has an internal structure. The outer layer is a thin crust. Inside of that is the mantle. And inside of that, we have the core. The outer and the inner core. Earth's three chemically distinct layers that make up the structure of its interior. Another huge idea is this concept of geologic time or deep time. So the Earth is 4.54 billion years old as calculated from meteorites that have been delivered from the asteroid belt and modern techniques of what is called radiometric dating, where we can put an exact timestamp on the age of rocks. This we'll talk about in detail, but using fossils and principles, we can get a relative age of rocks, and taking certain rocks and using radiometric dating, we create the geologic timescale, which is essentially the periodic table of elements for geology that helps us to locate things, locate events, locate rocks, locate fossils, understand evolution through time of the geologic record. It's pretty cool. After all this rock talk, rocks, plate tectonics, geologic time, we'll look at natural phenomenon carving Earth's surface. Here you see a river carving through some rock with some brown water here transporting sediment from a tributary. We'll focus on earthquakes, landslides or mass movements, rivers, glaciers, deserts, groundwater, coastlines, all of the surface features that are carving and creating the diversity of beautiful landscapes that you and I get to go enjoy and see and learn and study all along the way. So when we get to here in our course, we're at a pretty cool part because we've learned about minerals and rocks, we've learned about plate tectonics, we've learned about the structure of the Earth, and now using that fundamental knowledge, we get to go a little bit deeper into what are the processes that are acting on our Earth's surface. We'll tie it all together with a discussion on climate change. Climate change is a natural process and it happens throughout time. Climate change is also being impacted by anthropogenic, which is human impacts, specifically the burning of fossil fuels. And another one of my goals is to teach the science of climate change to students so that you understand how this process works in the space of our modern industrial applications and our energy usage so that you have fundamental knowledge for this conversation in the science of how it works. So we'll get big into climate change. This comes near the end of the semester. To conclude today's lecture on our introduction to physical geology, we'll study rocks, minerals, plate tectonics, geologic time, surface processes from rivers to glaciers to landslides and more. This will give us valuable insights into the forces that have sculpted our Earth's surface. And on a more esoteric note, learning about geology is like learning about yourself. It's like looking in a photo album of your childhood and saying, that was me when I was young. That's how I was. And understanding your childhood helps you to understand yourself now. Understanding our Earth's history, understanding how our Earth works, how it functions, because we are part of this Earth, we are part of nature, and when we can connect to our Earth in this kind of a way, we can connect deeper to ourselves. Learning geology is a practice of going home, of learning about yourself, and of loving yourself. And so with that, I'm really excited to go so deep into geologic time and all the geologic practices and principles with you this semester. Thank you so much, and I look forward to talking more geology with you soon.